Hey, what's up, pre-calculus? Today we're going to briefly go over a few ideas and concepts related to something called average rate of change, which I will abbreviate AROC, AROC. Well, Mr. Kerr's mom shared this table of me. It shows his height over the first 8 years of his life. So in part A, why don't we compute the average rate of change of Mr. Kerr's height from age 0 to age 2, and we'll be sure to include units when we report our answer. So what we'll be doing here is dividing the change in the y values divided by the change in the x values. That should remind you of the word slope from past. That symbol, the upside down triangle, that is the Greek letter delta. And in math and science, we tend to use that to describe the change in. Since we are doing this for not x and y specifically, but height and time, how about we reframe this here? Delta height, the change in height divided by delta time, the change in time. To get you used to some function notation here, always an important idea in pre-calc, why don't we also write this as h of 2 minus h of 0 over 2 minus 0. So now we can consult the chart and notice those values here. And if you take a calculator, divide them up real quick, let's see what we get. That comes out to 14.3 in the numerator, 2 in the denominator. For a real world situation, we do actually prefer a decimal value. Just makes things seem a little more understandable to our brains. So it turns out Mr. Kerr grew on average 7.15 inches per year when he was from 0 to 2 years old. So yes, could you try on your own and see what you get for that next part? Pause the video and catch up to me. Okay, welcome back, pre-calculus. Hopefully you have some values here that match what I've computed. H of 6 minus h of 4 all over 6 minus 4. Crank that out. Feel free to use a calculator, and from the time Mr. Kerr was 4 to 6, he grew on average 2.75 inches per year. Clearly, we can see we got different answers for what I gave you in part 1 and what I gave you in part 2, and we should naturally conclude from that humans don't grow at a constant rate over the entire duration of their childhood. In the first 2 years of his life, Mr. Kerr grew a lot faster than he did from when he was aged 4 to 6, and I bet if you go ask him about it now, I bet he doesn't grow anything at this time in his life. I bet he's just kind of stalled out growing. All right, why don't we take a look at what's down here and a little visual explanation of average rate of change. Average rate of change between any 2 points on the graph of a function will be the slope of the line through those 2 points. The line through 2 points on a curve is called a secant line. So I will show that secant line here in red. The secant line is, of course, a straight line, and it does have a slope. This curved function here, the curved graph of f of x, it does not have what we call a slope, but we could compute the average rate of change between these 2 points on the function. So I'm going to start labeling them. We'll call this x1, and I'm going to use function notation again. I'm not going to call that y1, I'm going to call that f of x1, and I'll call this point here x2, comma, f of x2. And yeah, there, right there, there's our secant line. Okay, so as I've been kind of showing you here, the average rate of change really just is the slope of that secant line. And we could call that, again, delta y, change in y, over delta x. And using the points and the function values that we've shown in this little diagram here, we can record that as f of x2 minus f of x1 over x2 minus x1. So it is basically the slope formula, but we are using it in a slightly more grown-up fashion with slightly fancier notation. So please make that adjustment from Algebra 1 and Algebra 2 up to where we are now. Okay? Same formula though, works the same. So just to summarize that, the average rate of change, AROC, of the function f of x on an interval that starts at x1 and ends at x2 will be right here. So please make sure you write this neatly, prominently, and correctly because it will be something important to remember. All right. Let's look at a little bit of the next example. So we do have the function graphed here. It is the graph of the function negative x cubed plus 5x, just a little visual here. And I'd like us to compute the average rate of change on the interval -3 to -1. So I'll call that my first x value x1. I'll call that my second x value x2. And in red on the graph, I've connected them, and that would be the secant line, and we are finding the slope of the secant line. So please, let's see here. I'll get you set up. I'm going to ask you to try this computation without me, because it is just slope, and you've all successfully completed Algebra 1 and Algebra 2. All right, so I'd like you to find these two function values, find the y values. You can put them right in for x and crank out the y, and then subtract and divide. I'll catch up to you in a moment. You do the math. All right, welcome back. I have the rest of that problem shown here for us. We have the y values. I happened to use the graphing calculator to compute the y. It just seemed a little bit easier, but you can certainly just crank that out mental math. But the values that I got, I've subtracted and divided. And unless it's a word problem, we really would want to report this as a reduced fraction instead of a decimal. But this one did not require such shenanigans. I would like you to try the next one there. You're computing the average rate of change from an x value of -2 to an x value of 1. So I'll show the secant line there in blue. You are computing that average rate of change. And just as a little tie into the physicality of this, we notice the secant line here is trending downwards, decreasing in the first part we did. And look, the slope of it was negative. As you compute on your own, the slope of that next secant line, you see it trending upward, and you should anticipate a positive answer. Try that out on your own, everybody. Okay, welcome back. So I've again used the graphing calculator to just save some time. I computed the y values, and as I ran my computation, I did get an AROC of 2, average rate of change of 2, and that does correspond to the positive slope. That's all for now. Ta-ta!